think that it might be what he's.
All right. Well, it gives me great pleasure to introduce Martin Flashman from Charles Poly Humboldt. Martin is here, as most of us know, to attend the History and Pedagogy of Mathematics Conference at UNSW. And Martin asked me a couple of days ago whether he'd be able to have an opportunity to present some of his work off schedule. And so Donna has been kind enough to find a space within her Learning and Seminar series for Martin to present. And thank you also, Martin, for putting your hand up. And I'm sure we're all going to be interested to hear more about your work on mapping diagrams, function visualization of real and complex analysis and matrix algebra. Over to you, Martin. Thank you.
Well, thank you very much, Jim, and thank you, Donna, for setting all this up, and thank you all for hanging out. I know you have a little time to refresh yourself before dinner. I am also a visitor at the University of Arizona in Tucson, and I'm thankful to be here rather than in the 110 degrees there, or 105 this afternoon. The work I'm giving is an extension of what I gave at the ICME conference in China. I did it remotely then, and there I only talked about the real and complex and didn't do the matrix algebra because it's a short presentation that I had here. And all of this is included in this GeoGebra book, and this is the link for it, so you don't have to remember anything too difficult. My name, tiny.us, and UNSW, which stands for something, I think. And I gave a presentation earlier this week about mapping diagrams related to work by Napier and Newton, and it's something that I work on a lot currently over the past 10 to 15 years, and recently in the past 5 years or so, I've made some really what I think are substantially new visualizations to what was already an extensive work that I had on calculus and mapping diagrams. So this is a GeoGebra book, and so when you get to it, you'll see that the top is UNSW's symbol, and each page has a next page indicated at the bottom. So when you actually do it, and on the side here is a full table of contents with individual sections. So we'll go to the next section, turn this down. So I'm going to focus on 3 areas. Mapping diagrams used in beginning algebra. So if I work with some teachers who are just working with beginning algebra students. And so one of the things that I found mapping diagrams to be very useful for is in visualizing the algebraic steps that students learn on how to solve simple linear equations of the form ax plus b equals c. And so, for example, we'll see how to solve 2x plus 3 equals 5. If you need something to do while I'm talking, you can always work on solving that if you can still. I'm also going to be looking at using mapping diagrams and studying complex numbers and visualizing complex linear functions. So I'm going to be emphasizing the linear here. I have work on complex functions that are quadratic and exponential and logarithmic, and about differentiation and integration in complex variables and how to visualize stuff like that. But I'm just going to stay with the simple so you can get a sense of the wows that are here, because as David told me when he saw this stuff, he says, when you see that complex thing, you're going to get a wow. So I hope you're all ready to do that when we get there. And then, so we're going to, as an example, we're going to look at f of z as a complex number 2i times z and what that looks like with a mapping diagram on the unit circle. That's complex numbers whose magnitude is 1. And then finally, in studying linear operators, transformations, and linear algebra, this is work that I did actually after the complex stuff. I started to think about linear algebra and think about linear operators on R2 in particular, but I actually have some stuff that does R3 to R3. But we'll just look at a linear operator of the form that's given by matrix. So the operator on V is the matrix times V. where it's a 2x2 real matrix. And the example we'll look at, one example for sure will be the matrix 2, 0, 0, 1 on vectors of magnitude 1. So again, the unit circle. So that's where we're going. And I'll give you a quick look at some of the stuff. So this is what I talked about in my Napier talk. This is Napier's treatment of how he defined logarithms. And he has two number lines, one in which something's moving arithmetically, and another a line segment in which the numbers, the point is moving with its length decreasing geometrically. So it's arithmetic versus geometric on two number lines. And time is in the background. And this actually is from, this picture is what Kathleen and Lindsay Montel put together in their discussion of that in the Napier presentation. And then this is actually Newton's writing. Well, I don't know. I didn't verify it with him. I could have called him last week, but I didn't check. But you see in the upper right hand corner, this is the way Newton was thinking about motion. And his two variables, he had two variables moving. Time as the background variable there, and the motions are kept track of with, again, letters keeping track of. So A corresponds to B, C corresponds to D, and so on down the line here. So there's a correspondence between points on the two lines. And that's what I consider, this is from Michael Spivak's calculus book. He has mapping diagrams in his so he has functions going from the bottom line to the top line, and this is constant, and this is a visualization of the cubic function. Another 20th century is work by Henry Giotto, who actually seems to say that I was influencing him, and he makes these tables and then he gives these charts to the students so they do them by hand. And it is a very good thing for students to do these by hand before they start using technology to fill them in. Recently, 2012, Larry Gonick, who has a series of cartoon guides to various pieces in science, did a cartoon guide. Calculus, he is a math, has a master's in math, I think. And so this is showing the diagrams compared to the graphs, and he shows how they put together, and he has some exercises for students to get familiar with these diagrams. And this is actually an interesting diagram here of a step function, understanding a step function. Also influenced by some stuff that I did was work by a group in England, University of Cambridge. Underground mathematics was a big project there for years until they lost their funding. And one of the people who was involved with that project went to a workshop I gave in England, and so he built these. These are really very nice. So this has got the arrows already for 2x plus 1, and see, I'll extend the line segment. He's got density, and you can zoom in. This is at 0, and I'll just show you quickly. This is very nice. You can just change that to a minus sign, and this will get a little ooh maybe. Haven't thought about this. What's going to happen when I make the minus sign? Anybody know? Crossing. It'll be crossing, but not just crossing. Single point. And you can have your students, or you can think about it yourself as to why that happens, or if you know projective geometry, it's duality. Linear function. And there's geometry behind it as well. This is pretty quick sort of illustrate. Here's a table, and here's a diagram that illustrates what's going on. So the basic idea is the inputs on the table are put out. I do mine vertically, not horizontally. There's reasons for that, but we don't need to go into those things. I think Spivak is upside down at least. But anyhow, so you have the value 0 here, so the value 0 here, and the output is the 2x plus 3 is 3. So you see 3 over here, and the arrow connects the input with the output. And I go from left to right, but if you're from a different culture, maybe you want to go from right to left. I go from bottom to top because I usually think about ground floor, first floor, second floor, third floor is going up. And so these are the levels that my number lines are doing in my mapping diagram. And I label the axes with X and maybe the value of the function or the letter Y. I want to distinguish that as I did, as it's done in the table. So let's talk about solving linear equations. And so frequently I give you time to solve that, write down your solution, show all your steps. And so people will do that, they'll write down the steps. Maybe they'll subtract 3 from both sides of the equation. Maybe they'll then divide by 2. So the basic idea here is to understand that the function 2x plus 3 in this equation is a function, and it's not sitting by itself, it's actually a composition. And when you get the students to check it, the solution, they first multiply by 2 and then add 5. And whenever you say and then, now you start to think about composition. And if students start to think about that in beginning algebra, they won't be so confused about composition when they get to calculus and somebody says, oh, now we need to know a real composition. They'll be doing it and thinking about it all the way. And mapping diagrams is a very good way to visualize composition. So here I have already multiplication by 2 already on my diagram. And I'm going to put up the composition. So that's adding 3. So multiplication by 2 is a magnification. Adding 3 is a translation. You see the composition here. And I'm going to take that composition out now. And I have ways to change the factor of n or the additive 3 here for later exemplary. But first, I just want to show you. So the first thing is the number 5. Where does the number 5 show up? It shows up here at the target. Because that's what you want to do. You want the number, you're going to put a number x in for x, multiply by 2, add 3, and the result is supposed to show up in the answer at 5. So that's over here on the axis. So first step, I think you all would say would be subtract 3. So I show that here. And subtracting 3, well, that means going back from where you were. So I need to know, how did I get to that 5? I have to reverse the process of adding 3. So I subtract 3, so the arrow is just going backwards on that. So we have a visualization of that additive inverse, subtracting 3, and we get 2x equals 2. So now I'm looking at number 2 and saying, how did that number 2 come up? Well, I have to find out how I got to 2 by multiplication. So multiplicative inverse of 2 is division by 2. That's the inverse function as well. So we're going to back up on that function by multiplying by 1/2, and we see the result is 1. And then we're not done. A lot of people think we're done. No, we're not done. That's just our only candidate. When you go backwards like this, you're finding possible suspects, but you have to check to see whether they actually committed the crime. So we'll check to see that when you put the 1 in for the x, you do get 2 plus 3, that's 5. And with GeoGebra, I can change the factor to 3. And now we see it multiplied by 3, we see division by 3, and we have estimates because, or I could make that 4. And now we see, but you see that the process is exactly the same. You see the visualizations exactly the same. So it works that way. I can also change the B. And see that the process is always the same. It's always reversing the arrows that we're seeing. It's the same, and that goes along with the arithmetic that we're doing in solving the algebra symbolically. So that's my first use of the mapping diagrams to visualize solving simple algebra problems. One could do this as well with quadratics. Not so easy with cubics because cubics are not compositions in this easy way, but you can do something for cubics this way. And lots of other things you can do as well. So let's look at complex functions now. Anyone have a question about the linear ones? I think that's pretty straightforward. So, well, this jumps right into it. So, usually complex numbers are visualized by points in a plane. the real axis is the x-axis, and the imaginary axis is the vertical axis, the y-axis, and the points are visualized by what appears in the plane. The functions, again, are usually treated as inputs and outputs, so you might have a table item. I don't think I have the table thing here. We're going right to the chart here. So the basic idea is I'm going to show you what a linear function looks like here. And the new thing is that historically, the planes would be a complex plane here, a complex plane here. This would be the domain, this would be the target, and you draw an arrow from a complex, say A plus BI to a point here, C plus DI. And this might be, this is Z, and this is F of Z. So that's the traditional mapping diagram that's used in textbooks. And I will mention David Powell and Ian Stewart's textbook on complex analysis as a reference because for several editions, that's the way they would visualize things. They had a very visual approach to complex analysis. And this nice book out on visual complex analysis. But they're all sitting on a page like this. And if you get a lot of arrows, it gets really hard to follow. So sometimes they just draw a curve here. Even in the technology that was around, you draw a curve and you'd see that curve come around here on whatever technique was going on. So you'd have curve corresponding to curve, but you couldn't draw arrows point to points. So what I did when GeoGebra came up with a 3D version of GeoGebra, I developed a way to do mapping diagrams with a 3D version. So this is my domain, and you see that's at the top here. And then the bottom is the target. And what I have in this picture is the image of a circle. This is the unit circle, and I can change the radius of the circle. I can also change the center of the circle. And what you see over here already visualized is the diagram. So we have the points on the top and the arrows going to the points on the bottom. And this is 3D. And if you, I didn't bring 3D glasses for everybody, but GeoGebra has a 3D feature to it for this thing. So you could make this 3D and put on your glasses and you would see 3D. See the art. So that's, we'll stop right there. Now, one of the things that I've done, which is not so easy to do in GeoGebra, so this is, it's all available in open source, so you can find out how I did it. But you see the complex number A here? Because this is F of Z is A plus BZ. And it's the A is at 2 and the B is at 0. Okay, so and F of 0 here, I have F of 0 as well. I can change and move F of 0 around here. Put this back here. That's showing up here. That's B, I'm sorry. I guess I don't have. Oh, that's Z sharp. So this is showing up in Z sharp at the center. So the center point is Z sharp. And the B, you see that the changing the B just adds B. So it's just translating the image. But the interesting thing is to take A, and I'm going to use my slider. I'm just going to slide it up here. And I'll move it over because we're going to multiply by 2i. You recall that was my problem. So there's I. Remember, 2 is magnification. So see. What that's. Slower. That's heads on. That's from the side. That's from the side. So you see different views, and this is back to the. A little bit. And that takes it back to general position. Well, I think that's enough of that picture. So you can see that this is a very different way to understand complex functions. And again, I can change the thing here. So now we're going to look at linear functions. I'll have time for questions and maybe explore some other functions. I have a bunch of other stuff at the end here. Sort of, if time permits. So hopefully we'll get through what was that originally was what I gave at the that's the 20 minutes that I had at ICME. A little bit more. So we've got a little more time. This is linear. So this is the traditional linear mapping diagram, for example. This is the 2, 0, 1, 0, 0, 1 that we're talking about. So this is going to magnify in the first component and leave the second component fixed. So we see the circle here transformed into an ellipse. That's linear operator on this circle. That's a traditional picture of it. So before we get to the R2 to R2, I wanted to show you a little bit about what R2 to R looks like, because those are sort of the linear maps that people talk about, a function of two variables, f of x, y equals 2x plus 3y. So that's the first linear function, that linear transformation that students might see, not thought of as a linear transformation, but just as linear in a Calc 2 course or a calculus course of several variables. And so you can think about that as also matrix in a product. It's 2, 3 in a product of 0, 1, giving us 3 here. And that's the general thing. So that's 1 is equal 3. And you can see the vector here being visualized. And this is again, so this is the plane being transformed to a line. And I think, I'm sure, there's the number 3. So every point on this line will be sent to the same point. We sent to 3. So this is the line 2x plus 3y equals 3. But the x and y at any point in this line, the vectors on this line, will be sent to the same number of 3. So it's the pre-image of 3. That's just, so that's a little bit. And if I wanted to set that to 0, make this down to 0 here. And that's, so 2x plus 3y is the null space of this linear transformation. But of course, when they're in a calculus course, before they've done linear algebra, that's just the level. Those are the level curves, and these are level curves for linear functions. So this is a more complicated thing. So now we have a matrix. I have an A, B, C, D. And so that gives you, I think I get, yeah, so that's A, X plus C. I got this mixed up here. Okay. These are the wrong ones. So it should be A, B, C, D, and then you have AX plus BY and CX plus D. So apologize for that error there. But it's done right in the actual. So in this thing, I don't particularly like sliders. Mathematica and a lot of the technology like sliders, but I did do this one with sliders. So I can change the A is 2.2. I can make that a 2. This is a 2, and B is -4, and we're gonna make that a 0. And then we have the C, it's gonna be the 0 again. And then the D is gonna be 1. And so this shows us the mapping diagram. That shows you what's happening to these two lines. And you see that this point here is on one line. And this is actually controlling the line. This is that shows you a vector on that line. And it shows you the parallel lines are sent to parallel lines in this visualization. And I can move this to different parallel lines, and I can change the. So this is showing some of the linear operators preserve the lines. At least if they're now singular, where this is. And next one I think is going to show. So this is the effects of different matrices. So this is these are not dynamic figures, but these are taken from this. So this is magnification by a factor of 2. So that's 2 times the identity here. This one here is the one we saw before, which magnifies the first component and leaves the second component fixed. And this one here is 1, 0, 0, -1, which is going to change when they flip it. It's a reflection. And of course, it's harder to see on those small pictures, but I think I have those set up here. So I have this one. This one I have a sliders as well. So I'll just show you. So this shows the span of so the vector V is here. And you see the span of its image here. Here's the circle image. And here's a square image. And if I change, you can see how that's affected by changing these dynamically. So that's the identity. That's very exciting. That is 0. This is minus. You can see that's got a reflection going on. You're not going to see the difference, but you can see the lines being reflected. But that's in the old style. And here's in the new style. Let's make that a -1 here. 1%. Here's the ellipse. Old style, new style. Let's just put a -1. So this is looks like it's the ellipse, but it's actually got a. If you look at it this way, you can see that it's got a reflection in it, which you can't see from this diagram, but it actually has a reflection going on as well. -1 or coin. So those are things that you can see. Features that you can see from the mapping diagram. This thing that you really can't see the traditional mapping diagram. This is again that we just saw. So this is a list of some references I gave at that time. This is Inselberg is the only other person I know who's done, he didn't do it, but in his book, Visual Multidimensional Geometry and its Applications, Parallel Coordinates, a student of his started work on this visualization for complex. He didn't get very far, and that's all there is in that book. That's the only other place I know. I don't think they've done anything else. Or Needham's Visual Complex Analysis is a terrific book, but I offered this stuff to him. He never even responded to my letters. Bit tall, and Ian Stewart did put some reference to these diagrams in the last edition of their complex analysis. They gave me about a page and a link to it online. There's the reference to it. It's the third edition. No, it's the second edition. Underground Mathematics. This is a link to their website. So I hope you will see the potential of mapping diagrams, and there's much more work that I still have to do on this stuff, but I got a lot done. If you'd like to learn more math diagrams, you can contact me by email. There's the link to this thing, and I'm going to move on now. If anyone has any questions, I'll answer them. I'll move on to some other examples from complex if you're interested. Or you can go where you fit. So this is a good place to take a break for questions. And then if you want to stay on, I'll show you some more pictures from complex.
Well, let's just thank you for what you've done. Thanks, Mark. That was great. Any questions?
Yes.
You did say earlier that if somebody asked, you would show how to visualize complex integration, which I find really hard to understand. So if you have an example of that, that'd be great.
Yeah, you can do. This checklist. So I thought you might ask that, so I have. Yeah, you get it. Okay, let me see if it's in. That's about minutes. So it's going to take me 1 second. So the definition of complex integral, I'll use a traditional definition that's 3-month sum based rather than relying on real line integral. So this is the complex line integral defined with real functions, not relying on any relying on complex functions, not relying on any real line integrals. And so this is the curve in the plane. It's cosine plus I sine by t. So it's going from 0 to 1 because I have the pi in there in the parameter. Okay, and this is the graph of the function. So the function here is z squared, so it's going around the whole circle. Okay, so that's the actual function. So now I want to show you the line integral of z squared around this curve. So what we see is the accumulation. That big enough? This is show you a little bit about the accumulation, so you can see that using more points, I'm moving around, and this is the estimate up here. So with 100 points, it looks like minus 2/3, pretty much minus 2/3, and that looks like it's going to be 0. So that's not so easy to see here, but here's the exact integral. So that's done because GeoGebra does have some symbolic algebra available to it, so I can use that to actually build that. That solution, and shows the work on the antiderivative. So let's put the integral back up here. And you can see that it was pretty good as an estimate. And so that one's okay, maybe that's not, let's go around, if we go all the way around, what should happen? We go around to 2 pi, if I go around the whole circle, what should the integral be? 0, right? Right, because it's closed curve, it's analytic. So let's just see what happens when we go. We came back to where it started. There's too many points, so let's take it. You see it wanders around the curve. Starts at 0, goes around. I haven't actually, I don't have I should put a thing in there so I can actually show you it accumulated.
Trace it around.
Yeah, I went twice around, but it came back to 0. When it was adding it. Function went twice around, no problem, we take that. Function went twice. The integral. Doing something different, it's accumulating. So when it went halfway around, it didn't accumulate to 0. It didn't go once around, it actually left it out to minus 2/3. Then it came back to minus 2. It's really a very different way to think about what's going on. It's really about the sums, and it's not playing the games of, trickery with Gauss with real integral theory or playing little pieces around Cauchy-Worcester. It's really showing you the actual integral. I can change the function. That's the power. All right, so this is so this function is z plus 1 over z minus 2, so it has a singularity. So the circle goes to a circle here, and if I move the circle, so we can see some of that singularity when it passes through 2. You can see something about the Moebius transformation there, in that the circle goes to a line because it went through the singularity. So this is another feature of this visualization. You can easily see how circles go to circles or lines depending on whether it passes through the singularity. That's a really nice piece of complex analysis. Of course, I don't want to integrate through the singularity, but I'm off the singularity. When I start, what should I get? Integral of this z plus 1 over z minus 2 on the unit circle? 0. There's the estimate. And that seems all right. So now let's move it so that it has Okay, so that's now the function has the singularity inside the circle. So the result should be. Anybody? 2 pi I. 2 pi I. Right, so let's see how we do. Okay, so that's with n equals 8. So we see it's going out someplace. Let's see the 2. That's where it's getting close to. And as I move this out further, oops, back. Are we getting? Well, it's not 2 pi I. Why not? Because it has to take the value of the z plus 1 and evaluate that at singularity and then multiply by 2 pi I. This is the Cauchy integral formula. If I made that numerator 1, then I would get 2 pi I. But here I get 2 pi I times 3. Z plus 1, the singularity is 2. So it's 2 plus 1 is 3. So it's 3 times. And that's what this is. 3 times.
What's the exact?
The exact one's going to go crazy because why does it go crazy? Because it's still going on. So it doesn't move up on the Riemann surface. So it's doing real integrals. It's doing a real thing. So it doesn't realize that this function is moving on the Riemann surface to do the integral. So it thinks it's 0. So if you did the evaluation using logarithms, you get an error. But that's the same error you get if you're a student. You try to do it with logarithms. It's the same.
Any other questions?
Yes.
Yeah, I have a comment on a couple of questions. A comment and a couple of questions.
Okay, comment and a
If
question.
you look in the complex plane, a function like a rotation, or
Yeah.
multiplying by a complex number of modulus 1, or which may be a root of unity or not. I
Yeah.
guess you get a nice image. And in fact, if you iterate, you'll get, according to your method, it seems to me a nice visualization of the dynamical system generated by the iteration.
You can do yeah, let me see if I have a composition.
For taking powers.
That seems great. Look at the see. I don't know if I have a composition here. I do have a composition, but the only place where I actually play the composition game is for quadratics.
It would be nice
Yeah.
to visualize.
So this is a visualization
Yeah.
of a quadratic function as a composition. So the function is given as a z minus h squared plus k. And the parameters are all here. And this one here is actually complex. So first thing is, so what is h? H is 1. So we see the circle being just shifted. And the next thing is to square it. And I guess we're gonna get to it. So this next one is the squaring. squaring there, and then there's another multiplication. And then finally, there's the shift. So, let's see, let's take the H down to 0. The H down to 0. So that's just throwing out the first figures. Now we just have the squaring function, and you can see the double covering that. Double covering happening there. And then, okay, so the A is multiplication by 2. So we see that magnification here of the circle, and then we have another shift of the circle. So this is a way to see the composition. Right. And now, let's solve. So I'm going to take out this for a second. So this is to solve the equation, when is that function equal to -2? So here it happens, and you can see the solution is given up here, but you can actually see that happening here. As you go back, you subtract 1, you divide by A is 2, so you divide by 2. And then you see the quadratic taking you to the square root of 2, and then you're just going back up. And so if I change the W, this is the value here. If I change the W, and then we see it going into complex roots. Those are all real. Yeah, now we get some complexes. But if I bring it up into the complexes, then you see that the roots which are here are not symmetric across the x-axis because the value that we have at the end is a complex number. So all of those things are going to be complex. You don't need the square root of a complex number. And that's not, those are not going to appear symmetrically across the x-axis. Those are going to appear diagonally. You still will have that point of middle. And if we start changing the A's to complexes, A's to complexes, you still have that symmetry about the roots with the origin. Anyhow, that's some of, you can see some of that in the composition. You get to see, and I don't have one that does something like compositions of quadratic that will show you either convergence or divergence of the points, which are things like
So Martin, I have one quick question.
Sure.
Maybe this is any other burning questions, we might finish with this one. Let me know. Just going back to your example of multiplying by 2i.
yeah.
So you had two sort of instances of the complex pattern. And it seemed to me that your visualization, that your arrows that you're sort of showing how one geometric object was being painted. That your arrows were doing quite a lot of sort of didactic work in a sense. That they were sort of,
Yeah, they tell you.
yeah, they tell you the story, but it's kind of what's interesting to me is that, well, they first of all, they're telling me a more compelling story than what you put on the board.
Well, yeah.
Yeah. But if perhaps we talk about transformation as rotating and scaling or something like that, I'm just wondering how you, if you're with a bunch of students, how you would explain that kind of didactic work that the arrows are doing with reference to rotating and scaling.
Yeah, so that's as the function. So I would, before I did the function, I would just deal with multiplication as without functional, just as an operation. So this is the kind of picture I had for the function multiplication. So
yeah.
So that's not with the diagram. That's just showing the interaction, and you can see that there's a rotation happening that depending on the angle here, this is being added to it and it changes. So that's that, and then the multiplication, you can see, by fixing this at one. Fixing this, two. Oh, that's working. Maybe this is. It's still magnification on the back and then it's, but you know. Actually explain why that's happening. You're going to, this is actually, these coordinates are actually given in a polar form. Or you can do that. These are not, yeah, they are, this is polar form. And the angles are there, so you can actually see how the angles are being added and the lengths of it. That's explained above, so that's from the text, but I would do that. So I do the geometry of multiplication before I did the function, so that then they could see that it's the z is being multiplied by the same constant, so it's the same rotation, it's the same magnification, and then the picture would make that clear as I take a circle and then move the circle around or enlarge the diameter, the radius of the circle to show that. So that's how I do that. And I did actually have this. I was teaching a course in complex analysis when I started doing this, so this was going on when the course was going on. These kind of images, I was just, 2 days before the class, I had this.
All right, well, I mean, you clearly have a very comprehensive library of,
Yeah, these are all on GeoGebra developers. So you can actually figure out how I did some of the stuff, because the ability to put a function in here, and just, that's something you can't do something that explains how that's done in a workshop I did at the end.
all right, well, thank you very much for sharing all of that, Martin. It was, right, yeah, that's
So if you
it.
have any questions, just email me. I can have that.
Okay, thank you, Donna.
Okay, thank you, Brett, Martin, and Jim for doing this. I'll stop recording.